Hey everybody, it's Ribley back again. Now we're going to talk about derivatives of polynomials and exponentials because we are done using me forcing you to use limit definitions of derivatives. Now that's a little dishonest on my part. You're still going to have to be able to do them, so don't just cast those aside. But it's time to get some rules, some power rules in place that we can use so that we don't have to go through taking derivatives of things like f of x equals sine of x by hand, by using limits. We want to be able to memorize some overall rules because this thing's not polynomial. I'm getting ahead of myself, but that's basically what these next few sections are about. Let's come up with rules for taking derivatives so that we don't have to use limit definitions anymore. However, we are going to use We're going to use the limit definition to prove some of the things that we're about to talk about. All right, so first and foremost, let's start easy. We're going to take the derivative of a constant. Well, if you think graphically rather than algebraically or numerically, excuse me, f of x equals a constant. It's just a horizontal line, is it not? Stupid email. It's just a horizontal line. This is y equals c. True? So remember, derivative is slope. It's instantaneous rate of change. Well, the instantaneous rate of change at any point on this function is its slope, which is 0. Likewise, if I take the derivative of a line, mx plus b, right? So let's change colors here real quick. So I've got some line. This is y equals mx plus b. Well, the instantaneous rate of change on this line is constant. And what is it? Well, it's easy. It's just the slope of the line. So this would be m. So if I take the derivative of x, it's going to be 1. If I take the derivative of 2x, it's going to be 2. If I take the derivative of negative 5/3 x plus 2, it's going to be negative 5/3, etc. All right, so we got those out of the way. We got constants, we got linears, and now we're going to take derivatives of any polynomial. But we're going to start really simple. We're going to start with the simplest polynomial. We're going to do the derivative of x to the n. Now, we've already played with limit definitions of derivatives of like x squared and x cubed. We know that the derivative of x squared is 2x. We know the derivative of x cubed is 3x squared. So the rule is this, but I'm going to prove it. All right, so everybody be nice. However, first things first, the rule is the derivative of x to the n, irrespective of what n is, all right, as long as n is a positive real. So we're talking about polynomials here, right, not rationals, is going to be nx to the n minus 1, okay? Now, let's prove it. So here's our proof. I want you to see this. I just don't want to I don't like just throwing out formulas and saying, oh, memorize the formulas and shut up, all right? So, you ready? We're going to take the limit as h goes to 0 of, now, what we have here is we've got x plus h to the n minus x to the n all over h. Now, what does this turn into? Well, hopefully you remember from back in the day, what we get when I get a binomial expansion, this thing is going to turn into, now let's look, the first term is going to be x to the n, and the last term is going to be plus h to the n. But what we end up with is we're going to get nx to the n minus 1 h plus n times n minus 1 over 2 x to the n minus 2 h squared plus dot 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 plus nx to the h to the n minus 1 plus h to the n. Now, where does all of this come from? Well, it comes from the binomial expansion. And I know that that's cheating just a little bit because that would assume that n were an integer, a positive integer. But this is the rule when we're dealing with any x plus h to the n. Okay, let me just do a little side note, and we can use, it's kind of cool because we can use Pascal's triangle. I forgot my h and I forgot my limit as h goes to infinity, or excuse me, as h goes to 0. But let's make sure that we understand this if I do a binomial expansion, all right? If I want to do x plus a, and I want to raise it to the 0, I get a 1. If I do x plus a to the first, I get, now what I'm going to do here is I'm just going to do the coefficients. I get a 1 and a 1. If I do x plus a squared, I get a 1, 2, 1. Remember, by Pascal's. Hopefully you've seen this before. If you haven't, it's a wonderful tool. If I do x plus a cubed, I get a 1, 3, 3, 1. The sum of those two produce the sum of these two numbers produce this, sum of these two produce this, etc., etc. If I do x plus a to the 4th, I would get a 1, 4, 6, 4, 1. This one drops straight down. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then I get that 1 coefficient at the end. Notice that whatever this value is right here, 4, 3, 2, 1, it always shows up in the second place. So x, oops, whoa, didn't mean to do that. So x plus a to the 5th, x plus a to the 5th is going to produce a 1, then a 5, then a 10, then another 10, then a 5, and a 1. Remember, these are just the coefficients. So that's where these terms come from. When I've got x plus h to the n, my first term is going to be x to the n. We should see that. That's where that 1 is. The coefficient of this is just a 1. The next coefficient is always n, and then I get x to the n minus 1, right? Because remember how this works. I reduce the power. This would become x squared plus 2ax plus a squared. I reduce the power of x by 1. This would become x cubed plus 3x squared a plus 3xa squared plus a cubed. Notice I'm reducing my powers from n, in this case 3, down to 0. Likewise, I'm not going to drag you through the drudgery of the rest, but that's where this term comes from. This term comes from, really, this is the formula for the sum of the first n terms, isn't it? We've seen this before. This is equal to n times n plus 1 plus, or over 2. Try again. N times n minus 1 over 2 is the sum of the first n minus 1 terms. And that's where we got this next term from every time. This guy right here is the sum of 1 plus 2 plus 3. This guy right here is the sum, where do I get this from? I'm getting this from 3, where am I? So, sorry, it's the sum of this guy plus this guy. That was confusing. I apologize for that. It's also the sum of these terms. Ooh, look at that. That's kind of fun. This guy right here is the sum of these terms. This guy is the sum of these terms. Sorry, I just geeked out a little bit there. Needless to say, these coefficients can be produced from Pascal, okay? But what's most important to realize here is, oh, you know what I forgot? I forgot my x to the n because that's this guy right here. Sorry about that. What's most important to realize is that the x to the n's cancel. Every other term is going to have an h in it. Notice that the exponents of h are growing. So I go from h to h squared to h cubed, dot, 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 up to h to the n. So when I cross out, I'm going to do this with red pen. When I cross out my h's, that h is now gone, that h is now gone. All of these other h's, I'm just going to take one off the top. So this is going to become h, the next term is going to be h cubed, the next term is going to be h to the 4th, dot, 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 all the way up to h to the n, whatever my n is. So when I take the limit as h goes to 0 of what's left, I get nx to the n minus 1 plus, now you ready, a bunch of terms with h's, right? My h canceled in the denominator, so I don't have to write that. Well, as h goes to 0, whoop, all of these cancel, become 0. And guess what? I end up with nx to the n minus 1. Now, you may say, whoa, what happened here? Well, think about this. This has no h. This is an n, not an h. I know my h's and n look very similar, but they're not. Okay? Now, here we go. What that means is, anytime that I'm taking just a derivative of a polynomial of an x to the n term, I now get to use that rule. So the derivative of x to the 10th is going to be 10x to the 9th. Could you imagine trying to do a limit definition on this of derivative? Watch, I would have to take the limit. as h went to 0 of x plus h to the 10th, ye gads, minus x to the 10th all over h. Now I don't have to. Now I have a rule. Now a cool ramification of this is, even if it's ugly, if I want to take the derivative of, say, I don't know, the square root of x, well, this is equal to the derivative of x to the 1/2, which is equal to, according to the rule, 1/2 x to the 1/2 minus 1, which is equal to 1/2 x to the negative 1/2, which is equal to 1 over 2 root x. Right? That's awesome. You are going to want to memorize that. Now, before I said we're only dealing with polynomials, but the coolest part of this rule is that the ramifications are far-reaching. How about the derivative of 1 over x? The derivative of 1 over x is the same as the derivative of x to the negative 1, isn't it? So the derivative of that, if I follow the rule, is negative 1 times x to the negative 1 minus 1, which is negative 2. This becomes negative 1 over x squared. I recommend highly, particularly if you don't have me in class, I recommend highly that you memorize these two derivatives so that you don't have to go through this process every time you take their derivatives. I very rarely say, just memorize it, but think of this as a vocab term that's going to show up in your sentences over and over and over again. It's really important, okay? Now, here we go. What if I want to take the derivative of, we're coming up with another rule. What if I want to take the derivative of a constant times a function? All right? In other words, what I'm saying is we can take the derivative of x to the 10th, but what happens if we want to take the derivative, I'll put it over, where am I going to put it? I'll put it over here. What if I want to take the derivative of 15x to the 10th? Well, I don't have a rule for that yet. So that's what I'm going to make right now. Well, how would this work? Let's look. This is equal to the limit as h goes to 0. And I have to show you this in the beginning because otherwise I'm just saying, oh, here it is. Now remember, the limit as h goes to 0 of f of x plus h. So this is just going to be c f of x plus h minus c f of x all over h. Well, remember, c is a constant, so I can factor it out. Not only can I factor it out of the numerator, but I can factor it out of the limit, because the limit of a constant times the function is the constant times the limit of the function. So this turns into c times the limit as h goes to 0 of f of x plus h minus f of x all over h, which if you look is just c times f prime of x, or c times dy over dx. In other words, the constant is along for the ride. It's just sitting there, and it's going to sit there the whole time that we take the derivative. So the derivative of 15x to the 10th is 150x to the 9th, because last I checked, 15 times 10 is 150. That's going to be really useful. You don't have to go through the process of saying, oh, this is 15 times 10x to the 9th. You just, whoop, you can run straight to that. I am not that sadistic. Okay, now how about the derivative of a sum or difference? This is going to be f of x plus or minus g of x. Well, what does your intuition say about this? The derivative of a sum or a difference? Well, let's look. This is going to equal the limit as h approaches 0 of f of x plus h plus or minus g of x plus h minus f of x plus or minus g of x all over h. Well, let's go up here. This is equal to what? Well, look what I can do. I can take f of x, right, minus, or excuse me, f of x plus h minus f of x. So this becomes f of, whoops, this becomes, I can group my terms, in other words. This becomes, where's my thing? There it is. Limit as h approaches 0. You know what? Just because I don't want to get too nutty kooky on this, let's just do it for plus and then suffice it to say that it works for minus. because otherwise my notation over here is going to get really confusing, and I don't want that to happen. I don't want to confuse you. Okay? So I'm doing, basically what I'm doing is I'm taking the derivative of a sum, and then we can remember that subtraction is just a sum with negative numbers. So I can extend this to the negatives. So I got this. Now all that I'm going to do here is I'm going to turn this into the limit as h approaches 0 of f of x plus h minus f of x plus g of x plus h minus g of x, if I distribute that negative across, whoops, all over h. And this is going to, well, look, I've got a common denominator, so I can bust this up. I can bust this up into the limit of f of x plus h minus f of x over h plus the limit of g of x plus h minus g of x over h, right? So I can turn this guy into the limit as h goes to 0 of f of x plus h minus f of x over h plus the limit as h goes to 0 of g of x plus h minus g of x all over h. And guess what I have? This is equal to f prime of x plus g prime of x, or the derivative of y with respect to x plus the derivative of f with respect to x plus the derivative of g with respect to x. Woo! Guess what? The derivative of a sum is the sum of the derivatives. So if I want to do f of x plus or minus g of x, this turns into f primed of x plus or minus g primed of x. I have it. Derivative sum of the derivatives. Derivative of a difference of derivatives. Now you may say, Ripley, oh, I'm getting so excited. How about the derivative of a product? Whoa, I don't know what just happened there. The derivative of a product, nah, that doesn't work. We're going to talk about the product in the quotient rule, and I'll explain why that is. That's kind of important, because if the derivative of a product were the product of the derivatives, think about that. That would imply if I want to take the derivative of 5x, well, wouldn't that imply that the product of the derivatives would always be 0? Here's why. What's the derivative of 5? Well, the derivative constant is 0. What's the derivative of x? That's 1. Well, last I checked, 0 times 1 was 0. So the derivative of a product is not the product of the derivatives. All right, so the last little chunk of derivatives that we want to be able to figure out are exponential functions. So we're going to figure out how to take the derivative of e to the x, and then we're going to generalize that, and we're going to cheat on this. I'm not going to lie to you. We're going to generalize that to a to the x. All right. Now, e is kind of a crazy number. E is defined as the limit as n goes to infinity. 1 plus 1 over n to the n. That is E, okay? This is how Euler defined it, E after Euler. Don't call him Euler, drives me nuts, which means, of course, you're going to call him Euler. Another way to define this is the limit as n goes to 0 of 1 plus n to the 1 over n. You can prove this with your calculator. If you want to throw these values in, as you get closer and closer to 0, you get closer and closer to 2.71828, blah, blah, blah. My favorite number, by the way, of all the transcendental irrationals. So I'm like pi. I like pi, don't get me wrong, but he's bomb. Okay, anyway, same thing here. You put huge numbers into this and you approach this, okay? Excuse me. Another way is, this is a weird way to define it, and you've probably never seen it, but E is the number such that the limit as h goes to 0 of e to the h minus 1 over h actually equals 1. I know that you've probably never seen a number defined that way before as the number such that something containing that number is true. Here's the thing, and you could the proving of this is kind of a pain in the butt. You can do it numerically. You can probably do it graphically, I think. But yeah, you could do it graphically. But if you look close at this, it's a very strange proof. Or excuse me, it's a very strange statement about E. However, if you were to put any other number other than E into this, then you wouldn't get 1. So it is a special way to define e, even though I'm not a huge fan. The difference is we get to use it to prove what the derivative of e to the x is. So let's figure out, let's figure out what f prime of x is for e to the x. This is going to be the limit as h goes to 0. I love it when I have a full page to work from because I know I'm almost done with the video and my writing doesn't really matter anymore. Remember f of x plus h minus f of x, so that's going to be e to the x plus h minus e to the x all over h. And this guy is going to be the limit as h goes to 0 of e to the x times e to the h minus e to the x. Now your spidey sense is probably starting to tingle a little bit in terms of why we used this guy right here. I'll just write this as the limit as h goes to 0 of e to the x times e to the h minus 1, that's e to the x by the way, e to the h minus 1 all over h. Now remember, as far as this limit is concerned, if it ain't an h, it's a constant. So this limit, even though you're like, Ripley, there's an e to the x there. We're not out of the woods yet, are we? Well, we are, because the limit as h goes to 0 of e to the x is just e to the x. Again, if it's not an h, the limit sees it as a constant. Excuse me, so I could actually write this as e to the x times the limit as h goes to 0, that's supposed to be an h, not an m, of e to the h minus 1 all over h. And voila! Guess what we get to use? This is e to the x times 1, which is e to the x. So the derivative of e to the x is indeed itself. Now, I'm going to extend this, and I'm going to cheat just a little bit. We will prove this in a few more topics. But I'm going to extend this to a to the x. I'll actually do this proof later. Well, remember, a to the x can be written as e to the natural log of a times x if I wanted to. But you guys don't have a really important key piece of information called the chain rule. But I'm going to give you a little heads up here because I want you to know this derivative and I want you to get an early start on it. It doesn't make a whole lot of sense to introduce the derivative of e to the x without a to the x. So this guy, I'm not going to go through a process here. I could, but we don't need to. Okay? Just suffice it to say that this is a to the x times the, not times ha, but times the natural log. Times the natural log of a. That's it. So it works with e to the x, right? Because the derivative of e to the x is e to the x times the natural log of e, which is 1. And that's how it works. All right. Now, so you've got some derivatives that I want you to memorize. You've got to know the derivative of e to the x. That's about the easiest one in the world. I would like you to memorize this even though you're not going to need it for a while. And then I want you to memorize the derivative of the square root of x, which is 1 over 2 root x. I want you to memorize the derivative of 1 over x, which is negative 1 over x squared. I'm not doing this to be sadistic. I'm doing it because it will make your lives much simpler as we progress into differential calculus. All right? All right, that's it. That's all I got, and I ain't got no more. Have a wonderful day, and I'll see you in the next section.